let's take a look now at the relationship between a general conservative force, f of x, and the potential energy function that goes along with it, u of x, in the general sense, using just the calculus relationships now between these variables. So let's see how that plays out. Well, we know that the work done by a conservative force equals negative the change in potential energy. That's from the basic definition of potential energy, being delta U equals negative the work done by the conservative force. And the calculus equation for work, if f is a function of x, we have to use integral f of x dx, and really that's it. We are done. So we have our integral f of x dx equals negative delta u, so delta u equals negative the integral of f of x dx, and if we recall what that means graphically when we integrate, is the area under the function, the area bounded by the function, and that f equals 0, horizontal line. So to calculate the change in potential energy, and please keep in mind, it is always the change in potential energy that we get when we take the area under the graph, will be that area, and you just throw a negative out in front. So that's it. So negative that area equals delta u. Now, what if we want the u of x function itself? Well, we have to be given the initial value, u initial, here, and then solve for u of x, because this is going to be final. We leave the final as a generalized variable, u of x minus u initial, which we have to be given. And if you look at the example I have shown for you down here, we're down here now, that what if you're asked to solve for u of x equals what if f of x is this polynomial function and you're told u initial equals 0? Remember, you have to be given u initial equals 0. Well, as I just said, you want to look at the generalized final position just representing an arbitrary x. So we don't lock the analysis window down. We leave it as a function of x. And we're going from 0 to x, negative that integral, integrate increase, x cubed on 3, x squared on 2. We lose the 3's and the 2's. Don't forget that minus out front. That's the biggest thing that students will usually forget if they forget something, that minus sign. So make sure that that is there. And then, of course, the integral of dx is x. So hopefully from calculus, you will recognize that as a not difficult integral of a polynomial and be able to get that answer. Now, you don't need to prove the fundamental theorem of integral calculus, the fact that differentiation undoes integration, and that they are essentially the inverse of each other. But from calculus, I hope you recall that the integrand, f of x in our integral above, can be extracted from that equation by taking the derivative of both sides. So negative du dx, right, will equal f of x. So if you have a u of x function, so we have our u of x function here, again, recalling the graphical representation of what your calculus was showing you, that f of x will then equal negative the slope of those tangents. So if you have a u of x function, again, my hope is your calculus and your ability to integrate and differentiate polynomials is in place at this point. If we have a u of x function that is a polynomial and you are asked to generate the f of x function that goes along with it, you simply take the derivative of that u of x function, you stick the negative out in front, and you are done. You box that then as your answer. If you are given a graphical version of this question, so if you're not shown the function itself, but you're just given this graph, you would estimate the slope, estimate a tangent line, calculate a slope, and represent that with the f is the negative of that slope after you would make the calculation for your estimate of the slope. So my hope is that all of this, in terms of the math that's involved here, sounds familiar to you. We've just put it within the structure of our potential energy function, U of x, and the conservative force that goes along with it.